Welcome back to the deep dive. Today, we're going to pull back the curtain on one of those digital tools you probably use without really a second thought, but one which hides an incredible amount of engineering ingenuity. Think about it. Have you ever needed to quickly share, like, a snippet of code or some text, maybe even an image online? You just paste it into a service like Pastebin, hit a button, and bam, instantly get a unique, shareable link.
Yeah, it feels super simple.
It feels incredibly simple, right? But beneath that seemingly effortless interaction lies this whole world of complex engineering, clever design choices.
And some really ingenious solutions for massive scale, actually.
Exactly. So our mission for this deep dive is clear. We're going to examine the sources you've provided to understand the foundational challenges and, the remarkable solutions involved in designing a system like Pastebin.
Right.
We'll extract the core insights from the requirements all the way to the detailed architecture. Give you a shortcut to understanding what makes these services tick.
Why they actually work so reliably.
Yeah, every single time. So let's unpack this. To start, maybe for anyone who isn't totally familiar, what exactly is a service like Pastebin?
Well, okay, at its core, a service like Pastebin is basically a web utility. It lets users store plain text, code snippets, sometimes even images just over the internet. The key thing, the real magic, is that once you upload your data, the system instantly spits out a unique, short, shareable URL.
Ah, the URL.
Yeah. And that makes it incredibly easy to share info with others. Often you don't even need an account, right?
Yeah.
No signing in.
Right.
You can think of it as a temporary kind of public shareable notepad, but one that's accessible globally with just a simple link. And it has to be pretty robust.
A temporary public notepad? I like that. Okay. So it sounds straightforward on the surface, paste text, get a link. But I'm already thinking, to make that actually useful and reliable and secure, there must be a ton of hidden requirements.
Oh, definitely.
What are the main functional and non-functional things we need to nail down right from the start?
You're absolutely right. There's way more beneath the surface, functionally speaking. Users have to be able to upload their data, text, images, whatever. And in return, they must get that unique URL. That's job one.
Okay.
Crucially, data should expire. Users often want stuff to vanish after maybe 10 minutes, an hour, a day, a month, or sometimes never.
So time limits are key.
Very key. We also need optional features, like letting users pick a custom alias, something memorable for their URL, and for sensitive stuff. Definitely need the option to mark pastes as private, requiring a password to get in.
Right. Privacy is huge. Okay. Those are the what it does things. What about the how well it does its stuff? The non-functional side.
Exactly. And those non-functional requirements, they're like paramount for user experience and just plain trust. First, reliability. Absolutely non-negotiable. No uploaded data should ever be lost.
Can you imagine?
Oh, I've seen the headaches when systems lose data. Even one little snippet. It just erodes trust instantly. Users get really upset.
Yeah, I bet.
Then there's low latency. Users expect things to be fast, near instant access to their pastes. So performance has to be snappy. Security is another big one, especially making sure those URLs aren't easily guessable. You don't want people stumbling onto private pastes.
Right. No predictable links.
Exactly. And finally, high availability.
Yeah.
The service needs to stay up, even if some servers, have issues or go down. Beyond those core things, we often look at extended requirements, like analytics. How many times was a paste accessed? Helps understand usage.
Useful data.
For sure. And maybe providing REST APIs so other developers or services can build on top of it or integrate it programmatically.
Wow. Okay, that's a really comprehensive list. Features, qualities. But turning that wish list into actual numbers, that's where the real design headaches start, right? Like, what kind of scale are we actually talking about? Users, data. This is where it gets really interesting.
Yeah, this is where we figure out what kind of beast we're actually building. Let's crunch some numbers based on the sources. For traffic, okay, a Pastebin-like service might see around 1 million new pastes uploaded per day.
1 million a day.
Wow. That breaks down to roughly 12 write requests, so 12 new pastes, every second.
Okay, 12 writes per second.
Now, pastes usually get read way more often than they're written. The sources suggest a pretty typical read-to-write ratio of maybe 5 to 1.
5 reads for every write.
Exactly. Yeah. So for every paste created, it gets accessed about 5 times on average. That means we're looking at 5 million read requests per day, which works out to about 58 reads every second.
58 reads a second, okay.
And that 5.1 ratio, it's like fundamental for the whole design. It tells us right away we need to optimize heavily for fast reads, for getting data out quickly.
Right, optimize for retrieval. Okay, 12 writes, 58 reads a second. That's constant activity. What does that mean for, like, storage? How much space do we need?
Good question. Storage. If we assume an average page size is, say, 10 kilobytes,
Which seems reasonable. Most aren't huge files.
right, users can upload up to 10 megs, but most are way smaller. So 10 kbb average, a million of those per day means 10 gigabytes of new data every single day.
10 gigs a day.
Yep. Over 10 years, you're looking at roughly 3.6 terabytes of storage for maybe 3.6 billion pastes.
3.6 terabytes. Okay, that's starting to sound significant.
It is. And don't forget the unique IDs themselves, the URL hashes. They're short, maybe 6 characters, but storing billions of them, even with metadata overhead. You'd need maybe around 22 gigabytes just for the keys over 10 years.
Huh, just for the keys.
Yeah, these numbers might not sound like, Netflix level huge, but they absolutely demand scalable and efficient storage. You can't just use any old database.
Right. Okay, terabytes of data, billions of records. What about the network side, the bandwidth?
Bandwidth is also really important to estimate. It affects our network pipes. For writes, 12 pastes per second, each 10 KB. That's about 120 kilobytes per second of incoming data ingress.
Okay, 120 kbs in.
For reads, 58 requests per second, each 10 KB. That's roughly 0.6 megabytes per second of outgoing data. Egress.
0.6 megs out, so more going out than coming in, which makes sense with the 5.1 ratio.
Exactly. Now, these numbers, they're pretty manageable for a modern setup, but they're still vital for network planning. Got to have enough capacity. And lastly, memory. For caching. This is huge for performance, especially with all those reads.
Right, caching the popular stuff.
Precisely. If we cache, say, 20% of the hot pastes, the ones getting most of those 5 million daily reads, we'd need about 10 gigabytes of RAM just to keep those popular pastes ready for instant access.
10 gigs of RAM just for the cache.
Okay, this is starting to paint a picture. So we've got our wish list. We understand the scale, billions of pastes, terabytes of data, millions of reads. It's a big job. So where do we even begin? How do we start sketching the actual blueprint for building this thing? What are the foundational pieces?
Absolutely. Building this starts with a high-level design. The big picture. Typically, you've got clients that's the user's browser or maybe an app talking to an application server. The main brain.
Kind of, yeah. It handles the logic, but it doesn't store everything itself. It talks to two separate kinds of storage. First, metadata storage. This holds the info about the paste, its unique URL hash, who made it, when it expires, things like that.
Okay, the about data.
Right. And second, object storage. This is where the actual paste content lives, especially if it's larger.
So the text itself or the image file?
Exactly. Separating those is really common for scaling. Now, the core operations, they're exposed through system APIs. Think of them as the public functions. We'd have something like create paste for uploads, get paste to retrieve stuff, and delete paste for removal.
Standard CRUD-like operations.
Pretty much. These APIs take parameters, like an app-a-dev key for developers, the paste content itself, the expiration length, maybe a flag for private pastes, and the system responds with either the unique URL or, an error if something went wrong.
Okay, that makes sense. Separating metadata and content storage seems smart. What about the database structure itself? How do we organize that metadata?
Good question. For the database design, we typically need two main tables, at least to start. First, a paste table. This holds the critical details. A unique paste date, the URL hash that's the short identifier in the link, like a tiny URL key.
Right, the thing the user sees.
Exactly. Then maybe the content itself, or just a pointer, a reference, to where it lives in object storage.
Ah, okay, so maybe not the whole 10 MB file in the main database.
Probably not for large pastes, yeah. Also the expiration date, created date, and maybe a user id if it's tied to an account. Second table is simpler. A user table. Just basic stuff like user id, name, email.
Got it. Paste info and user info.
Right. And that paste table needs to handle billions of records eventually. The metadata for each record isn't huge, but the number of records is the challenge. Which brings up a really important question. How do you guarantee a unique and short URL for every single paste? And do it fast enough, like 12 times a second, without collisions?
Yeah, that sounds tricky. If two people paste at the exact same microsecond, how do you avoid giving them the same URL? That would be bad.
Very bad. You could overwrite content, or worse, expose private data. This is where a dedicated key generation service, KGS, comes in. It's a specialized component.
Okay, a KGS.
Yeah. Think of it like a machine that pre-generates millions of unique, short random strings, like ABCXYZ, usually 6 characters using letters and numbers. It generates these in advance and keeps them in a big pool ready to be used.
Ah, pre-generation. So it's not generating them on the fly for each paste.
Exactly. Trying to generate a random string and then check if it's already been used every single time someone pastes. That would become a massive bottleneck.
Yeah, especially at 12 per second.
Right, it would slow everything down, cause errors. So the application server just asks the KGS, hey, give me a unique key. And the KGS hands one over instantly from its pre-generated stash.
Smart. Like grabbing a ticket number.
Kind of, yeah. And to make sure the KGS itself doesn't become a single point of failure if it goes down, nobody can paste. You replicate it across multiple servers. High availability for the KGS, too.
Okay, so the KGS pre-stamps unique IDs. That's clever for speed. But, okay, we've got the core pieces, the KGS. But managing billions of pastes, ensuring they're always there, always fast, always secure, that takes more than just the basics, right? What advanced stuff do we need to bolt on to make this truly robust and efficient?
You're right, the basics get us started. But to handle that scale and meet those non-functional requirements, we need more sophisticated layers. Let's dig into the data store layer again. For the metadata, the about data, you could use a traditional relational database like MySQL. They're great for consistency. However, when you're talking billions of pastes and need super fast lookups based on that short URL hash, a distributed key value store often shines. Think Amazon DynamoDB or something similar.
Why is that better here?
They're specifically built for massive scale and really fast, simple read-write operations based on a key. Perfect for get me the metadata for this hash. And for the actual paste content. Storing potentially large text blobs or images in a primary database gets expensive and inefficient fast. That's why we lean heavily on object storage, like Amazon S3.
The cloud hard drive thing.
Exactly. It's super scalable, highly durable, and way more cost-effective for storing large amounts of static data like paste content. You just store a reference to the S3 object in your metadata database.
Gotcha. Keeps the main database lean and fast. What about refining those short links? You mentioned 6 characters.
Right, the short link generation, we often use Base62 encoding.
Base62.
Yeah, it uses numbers, 09, lowercase letters, AZ, and uppercase letters, AZ. That gives you 62 possible characters for each position in the string. It lets you pack way more unique combinations into a short 6-character string compared to just using, say, numbers. Billions of possibilities without making the URL super long.
Maximizes the possibilities in a short space.
Exactly. Some systems might even generate a unique fingerprint of the paste content itself using an algorithm like MD5, then encode that into Base62. But no matter how you generate it, rigorous collision detection is key. The KGS helps a lot, but you still need mechanisms to ensure absolutely no duplicates slip through, ever.
Makes sense. Okay, smart storage, smart keys. What about handling all the user requests and speeding things up?
Right, performance and availability. First up, load balancers. They sit out front, taking all the incoming user requests and smartly distributing them across multiple application servers.
Spreading the load?
Yep, prevents any single server from getting overloaded. Ensures high availability if one server fails, the load balancer just sends traffic to the healthy ones, and better performance overall.
Okay.
Then there's caching. This is absolutely essential, especially with our 5.1 read-heavy traffic. We use a memory cache, maybe Redis or memcached. It stores copies of the most frequently accessed pastes, the hot ones, right in the server's RAM.
So popular pastes load instantly.
Pretty much. Instead of hitting the database every time for that super popular paste, the server just grabs it from its super fast memory cache. Huge speed boost.
Nice.
And we can take caching even further with a content delivery network, CDN. A CDN stores copies of static assets, or maybe even popular read-only pastes, on servers located all around the world, geographically closer to the users.
So if I'm in London, I get the paste from a London server.
Ideally, yeah, or somewhere nearby in Europe. It cuts down the network latency, shaving off milliseconds, which really matters for user experience, especially globally.
Okay, load balancing, caching, CDN, distributing work and data. But with billions of pastes, how do we stop the database itself from grinding to a halt? Even a key value store.
Great question. That's where data partitioning or sharding comes in. Instead of one massive database holding everything, we intelligently split the data across many smaller, more manageable database instances or shards.
Like slicing up a giant pie.
Exactly. Each shard holds a subset of the data, maybe based on the paste ID range or the user ID. This allows the database load to be distributed across many machines. And alongside partitioning, we use replication. We make copies of the data, including copies of each shard, on different servers.
For backup.
For backup, yes, but also for fault tolerance and read scalability. If one database server holding a shard fails, a replica can take over instantly.
Yeah.
Prevents downtime and data loss. You can also direct read traffic to replicas to spread the load further.
Partitioning and replication. Got it. What about all the old pastes that expire?
Ah, yes. Purging or database cleanup. This is critical housekeeping. You need a background process like a dedicated job that regularly scans the database, finds pastes whose expiration date has passed, and then deletes them from both the metadata store and the object storage.
Got to take out the trash.
Pretty much. Otherwise, your storage costs balloon and performance can degrade as the database gets cluttered with useless old data.
Makes sense. Okay, one last piece. You mentioned security and analytics earlier. How do they fit in?
Right. For security and permissions beyond just non-guessable URLs, we need robust API key management if we offer APIs. And for those private password-protected pastes, we need strong authentication and authorization. Verify the password, make sure only the right person sees it. Absolute must-have.
For sure.
And finally, analytics. We need a way to understand how the system is being used. This often involves collecting logs from all the components and processing them, maybe using a framework like MapReduce, which is designed for handling huge data sets in parallel. It helps us gather insights on usage patterns, traffic, popular content, identify bottlenecks, and basically plan for future growth or improvements.
Wow. Okay. It's genuinely incredible. It's so easy to just click paste and share and think nothing of it, almost like magic. But seeing all this laid out, the scale, the components, the caching, partitioning, KGS, the depth of engineering is just astounding. So what's the big takeaway here for our listener? Why should they, care about all this complexity behind a simple tool like Pastebin?
Well, what's really fascinating, I think, is that even something that seems so simple, like sharing text online, it actually requires this incredibly sophisticated dance between all these different technologies and design choices. For you, the user, all this complexity is precisely what guarantees that when you hit paste, your stuff gets stored reliably, you can access it quickly, and that unique link actually works every time.
Right. It's the hidden foundation.
Exactly. It ensures your experience is seamless, it's secure, it's fast, even when potentially millions or billions of other people are doing the same thing. It's really all that invisible engineering that makes our digital world function so effortlessly, so reliably day in and day out. Without it, those simple clicks just wouldn't scale.
And just like that, another deep dive comes to a close. We've gone from just a simple text box to this massive distributed system, billions of requests, terabytes of data, this whole intricate dance of components. Thank you for joining us on this exploration of system design. It's been really illuminating.
Yeah, it's fascinating stuff. It really shows that behind pretty much every smooth user experience online, there's a really thoughtful, layered, and often very clever design at work.
Yeah.
And if you connect this to the bigger picture, you see these fundamental principles: scalability, reliability, security being applied everywhere in countless services you use every day. It's what makes them work.
So what does this all mean for you listening? Well, maybe next time you use a simple online tool, you'll pause for a second and think about that intricate machinery. All those brilliant minds working silently behind the scenes, making sure your data is where it needs to be right when you need it. It's really a testament to the power of great system design.
Absolutely. And maybe a final thought to mull over. When you're designing any system, even one that seems really simple on the surface, thinking about the expected scale and where things might break right from the very beginning, that can save you a world of pain later on. It's not just about building something that works now, but building it to last, to grow, and to handle the unexpected gracefully.